Optimizing gangue rejection in mineral processing with geostatistics.
Can you imagine we are living without nickel, cobalt, copper, lead, zinc, etc.? Do you know where those commodities come from? Mine site where mining is performed is where those are produced. However, the productivity of the mining industry has shown a sign of a slowdown, one of which is contributed by the large energy consumption in mineral processing plant located in the mine site. At 4 gold and 3 iron ore mines, the average total energy required for the whole mineral processing plant is estimated to be around 21,000 kWh per kiloton. 21,000 kWh per kiloton is equal to 0.029 energy yield of the Little Boy nuclear bomb. At the mineral processing plant itself, this is mainly attributable to the higher cost of size reduction process consisting of crushing and grinding. In the mineral processing plant, crushing and grinding are often located at the early stage of processing step. Therefore, an early gangue rejection strategy to decrease the cost and improve the efficiency of the size reduction process is thought essential for a more viable mining operation. This strategy will shift our way of thinking in treating the material, from processing everything to selectively process the valuable mineral only or reject or remove the gangue or impurities as early as possible. Interestingly, as we fit the system early enough and probably skipping the further combination circuit, we can remove the gangue or impurities material still in coarse or big size, so that this strategy is called early coarse gangue rejection. As a result, our process will only process less number of waste, or we can double the high quality materials. By applying this strategy, we can have higher feed grade with selective material to be processed further, reduction cost per metal production, water conservation on further treatment, less chemicals used on further separation and purification, and less waste generated as less materials reacted with chemicals that have to be discharged to the environment. Interestingly, nowadays the application of early coarse gangue rejection is dominated with the process called sensor-based sorting, where a sensor is equipped to the sorting machine. Even though saving at least 30% energy, as implemented in Castle Mine, Goldfields, Ballarat gold plant, this machine has an ability to process high feed tonnage and high capital and operating costs associated with installation and maintenance of the device. Another method that is very potential with their simplicity, low capital and operating costs, as well as potential applications to various types of ores containing gold, copper, and nickel is gravity separation. However, this gravity-based gangue rejection method only relies on density. As we would like to have better grade of material, we also need to consider grade to be more selective. Not only that, but we also need to consider size for this whole process to be considered as early coarse gangue rejection. Unfortunately, to deal with the three factors, size, grade, and density, we require tons of materials for testing process. Therefore, we do apply the principle of early coarse gangue rejection in our testing process by using statistical analysis. Wilkie 2016 explained that distribution of 3,000 rocky particles with 66 rocky particles is similar. This then led us to think that we can vary small number of samples but similar result with bunch or even tons of materials to be processed. However, it has this sensor-based sorting, not in gravity separation process. By applying the same statistical approach, we then tested on gravity separation using Archimedes' principle, where the rocks were placed in the water, and validated the results obtained with the laboratory-based experiment where high-density liquid medium was used. At our statistical approach, not only we tested gravity separation, but also we incorporated all the main factors determining the better separation process, which are size, grade, and density. This approach has made gravity separation very potential to be applied for early coarse gangue rejection. Our findings shows that there is a large correlation between size, grade, and density of particles while incorporated together in one gravity separation system. We also found that not only grade, but density also influence with the different characteristic of chemical elements inside the rock particles in a multivariable linear trend, which then determine the selectivity of the separation. We also found that we need 13 optimized algorithms to be applied based on the basic statistical distribution. So far, to mimic the laboratory results when testing in bulk systems, the grade of a certain number of individual particles from the density measurement using Archimedes' principle should match the grade of the Gerard bulk sample at the constant particle density, even though this is not proven in border trial testing. Therefore, we are still working now and in the future to optimize the statistical model to be closer to the experimental one. In the long term, we hope that our algorithm can be applied in the gravity-based separation machine so that we will have more impacts on society and industry as well as create a prototype. This will then benefit society in terms of the safe environment where less chemical waste is produced. In specific, industry can save the consumption of water and emission could be reduced by 7% and 4%. Industry is the one that benefits a lot from this project. They are not only getting the benefit of early course gangue rejection as mentioned in the beginning. By applying this tactical advancement, particularly for the mine that is at development stage, they can remove the tertiary pressure circuit which at least save 480 to 9,600 kWh. Importantly, they can also simplify their way of thinking in making decisions as the less sample involved. For the individual engineer or researcher, laboratory testing for optimization can be easier and less laborious as there are less material to be treated. Our tests on manures prove that we can test apply this advancement to manures such as nickel, cobalt, copper, lead, zinc, gold, and many others. Therefore, there will be many mines involved. In Indonesia, we have Vale Indonesia, Freeport Indonesia, and Antam. In Malaysia, we have Angka Alam Jaya and Linas Rare Earths. In Thailand, we have Padang Industry Public Company Limited and Akara Resource Public Company Limited. With this technological advancement, we can be more sustainable. Like us, when we carefully process only selected materials and reject unimportant ones, it is the same to our future world. Our careful and selective choice now will determine the better surrounding and the better living we have. Will you join us? Together we can.